In my earlier video, I had discussed about idempotent operator and some question based on idempotent operator which had come in different type of competitive exam. Actually, today I will discuss nilpotent operator. The question is AB 3x3 nilpotent matrix, then which of the following statement are necessarily true? Option 1, I plus a to the power n equal to I for some n greater than 0 where I is the identity matrix. Option 2, column space of the matrix A is singleton set 0. Option 3, eigenvalue of the matrix A are of root 1. Option 4, A cube is a diagonalizable. For this option, 1 obviously true option because I plus a to the power n equal to I for some n greater than 0 where I is identity matrix. For this, consider AB non-zero 3x3 nilpotent matrix of order K and consider index of the matrix is 2. That means since I have considered it, index of the matrix is 2. That means A square equal to 0. And since A square equal to 0, so that implies a to the power m equal to 0 for all m belongs to natural number where m greater than equal to 2. Consider I plus a to the power n equal to I for some positive integer n. From this expression, it implies identity plus nc1a plus nc2a square up to ncn a to the power n equal to I. Since a to the power m equal to 0 for all m belongs to natural number and m greater than equal to 2, that means all part would be 0. Since A is non-zero matrix and A square equal to 0 but other part not equal to 0. So nc1 means obviously n times A and other part would be 0. Therefore, I plus na equal to I and that implies na equal to 0 and na equal to 0 imply A equal to 0. Are you getting the option OA? So, obviously option 1 is a right option. I plus a to the power n equal to I for some n greater than equal to 0 where I is the identity matrix. Option 2 imply column space of the matrix is 0. Is it true option? Notice, for this I will consider one example. For this, consider this matrix. And we all of us know, column space of the matrix is subspace which is generated by column. And obviously this would be the linearly independent column. Notice, here column space is generated by this column and this column. And here only linearly independent column is this 1 0 0. So column space is generated by only third column 1 0 0 which is obviously non-zero column. Option 2 is a wrong option. Column space of the matrix is singleton set 0. This is not true. Example, we can verify option 2 is not true. Here column space is generated by non-zero column, but the matrix is obviously 3x3 nilpotent matrix. Option 3 indicate the eigenvalue of the matrix are of root 1. Option 3 also not true because we all of us know the eigenvalue of nilpotent matrix always be 0. So eigenvalue of root 1, this is not true. And option 4 indicate a cube is diagonalizable. This is obviously true. It's actually the basic concept of nilpotent matrix. Just verify. For this, a cube is diagonalizable for nilpotent matrix. This is always true. For this, consider A is zero matrix or index K matrix, where obviously index of this matrix would be less than equal to 3 because A is 3 cross 3 nilpotent matrix. At first, if we consider A equal to 0, then obviously A cube equal to 0 and obviously this matrix is diagonalizable. Otherwise, once we all of us know nilpotent matrix is diagonalizable when it contains only 0 matrix. Since here A cube equal to 0 matrix, so obviously it is diagonalizable. Now consider matrix A is of index 2, and since A is of index 2, that implies A square equal to 0, and since A square equal to 0, that means obviously A cube equal to 0. So since A cube contains null matrix, so obviously the matrix A cube is diagonalizable. Another possibility is consider A is index 3. Then that implies obviously A cube equal to 0. And since A cube equal to 0, so obviously we all of us know nilpotent matrix is diagonalizable only when it contains null matrix. So it is obviously be diagonalizable. That means if we consider non-null matrix, but A cube always would be diagonalizable, because since in the question has indicate A be 3 cross 3 nilpotent matrix, that means obviously always A cube would be equal to 0. So option 4 is a right option. Are you getting the option? Now we will discuss another important question of nilpotent operator, which had come CSIR NET February 2020 exam. This is also very basic question which depend on the properties of nilpotent operator. The question is, consider a matrix M belongs to M in R such that this matrix is not equal to 0, and here M square equal to 0. That means here this matrix is nilpotent matrix of index 2. Then which of the following statements are true? Option 1, if n is even, then dimension of column space less than dimension of null space of this matrix. Option 2, if n is even, then dimension of column space of the matrix is less than equal to dimension of null space of this matrix. Option 3, if n is odd, then dimension of column space of the matrix less than dimension of null space of the matrix. Option 4, if n is odd, then dimension of column space of this matrix greater than dimension of null space of this matrix. We all of us know for nilpotent matrix, dimension of column space always less than dimension of null space. Here M is n cross n matrix such that M not equal to 0 and M square equal to 0. That means here the minimal polynomial is x square. So notice this is very important part here for this question. So obviously Jordan canonical form of this matrix can be either 2 or 1. If n is even number, then obviously Jordan canonical form would be such type. This part would be 0, 0, 1, 0, 0. Only 2 blocks exist. this type of matrix, this would be continued. And because here the order of the matrix is n cross n, so rank of the matrix would be n over 2. Also, null space of the matrix would be, for this matrix, n over 2. So notice here dimension of column space always same as dimension of null space when n is even number. But when n is odd, so possible Jordan block. Here, notice if we consider two block and other one block, then M would be similar to this matrix. And notice here there exists only one block of order 2 and other block all of order 1. So there exists only element be 0. If we consider only one block of order 2 when n is odd, then notice obviously rank of this matrix is 1. Then dimension of column space would be 1 and dimension of null space would be n minus 1. So obviously dimension of column space less than dimension of null space. Also, when n is odd number, so all other case, not only for this case, all other considerable matrices, always dimension of column space of this matrix always would be strictly less than dimension of null space of this matrix. M is similar to various type of matrix when n is odd number, but since n is odd number, at least there exists one block always would be exist since n is odd number. That means, and for all case when n is odd number, rank of this matrix would be n minus 1 over 2 and other column contains in 0. So null space of this matrix would be n minus 1 over 2. This is obviously true, and also one extra column would be exist, because when n is odd number, then there exists at least one block always would be exist. So here plus 1. That means when n is odd number, then dimension of column space always would be strictly less than dimension of null space. When n is even number, then dimension of column space always similar to dimension of null space. Come back option. Here, if n is even, then dimension of column space less than dimension of null space. This is wrong option. And notice option 2. Here, if n is even, then dimension of column space less than equal to dimension of null space. This is true option, because here equal to notation has used here. And option 3, if n is odd, then dimension of column space of the matrix always less than dimension of null space of the matrix. This is obviously true, and that means option 4 is wrong option. Now I will see another approach of this solution, because our goal is not only solve any question, our goal is how we will gain knowledge for higher study. This is basic approach. M is M cross N matrix, then we all of us know rank of this matrix plus nullity of this matrix is equal to N, and if A, B matrices of size m cross p and p cross n respectively, then rank of AB always greater than equal to rank of A plus rank of B minus P. Okay, and here A equal to B equal to M because nilpotent matrix, and given m square equal to 0. Then this would be reduces by this formula, rank of m square greater than equal to rank of m plus rank of m minus n. Understood why I have considered A equal to B equal to m? Okay. Then since given m square equal to 0, then it would be 0 greater than equal to 2 rank of m minus n. That means from this line, this implies rank of m less than equal to n over 2. Okay. Also, since rank of m plus nullity of m equal to n, and since rank of m less than equal to n over 2, that means nullity of m always would be greater than equal to n minus n over 2. That implies nullity of m always would be greater than equal to n over 2. So, for nilpotent matrix, always null space of this matrix is greater than equal to rank of this matrix, and this is actual proof. Okay, OL. And for odd, consider n equal to 5. Then rank of m would be greater than equal to 2.5. So we all of us know rank always be integer. So 2.5 cannot possible. Rank of this matrix always greater than equal to 2. But here order of the matrix is 5. Since rank greater than equal to 2, that means nullity of this matrix can be less than equal to 3. Are you getting? This is okay. Here I have considered it n equal to 5. But for order n, rank of the matrix would be when n is even n minus 1 over 2 and n minus 1 over 2. This is always be integer. So this is actually reduces to integer, and then rank less than equal to n minus 1 over 2. Then nullity of m always would be greater than equal to n minus 1 over 2 plus 1. Nullity always would be greater than equal to such type. From this line, this would be n plus 1 over 2. So rank of m strictly less than n minus 1 over 2, who is, sorry, not strictly less than equal to n minus 1 over 2. This is strictly less than always n plus 1 over 2, and this part would be always less than equal to nullity of m. For nilpotent operator, rank of this matrix always less than equal to null space of the matrix, and since I have got here the strictly notation, so when n is odd number, then rank of this matrix always strictly less than nullity of this matrix. Are you getting? When n is a odd number, then why rank of the matrix always strictly less than nullity of this matrix? This is another way, and this is also another way. I think this way is very easy and very conceptual. Okay? Oh, yeah.